Cyclic loading is the repetitive or fluctuating stressing of a material which degrades soil strength through fatigue. This research presentation focuses on the effects of such loading on soil strength with an emphasis on sand as per the research outlined in our key investigative literary sources. Various influencing factors have been recognised to significantly impact the degree of cyclic fatigue, and the means by which these influencing factors have been tested and identified will be explored in detail. Additionally, the implications of these influencing factors towards engineering applications, mainly focusing on consequences of liquefaction and footing design, will also be discussed.
The first paper investigated began by identifying the need for further study into cyclic behaviour of soils at a large number of cycles. The authors used triaxial testing equipment, as shown in the figure, to derive a high cycle strain accumulation model in an attempt to describe the behaviour of the soil at a large number of cycles. Various factors were studied, including the strain amplitude, average stress, density, frequency, number of cycles, and grain size distribution. The effects of each factor were then modelled, which have been summarised into the table shown. This article, published in 2020, focuses on the effect of varying loading frequencies on the liquefaction behaviour of sand, both loose and dense. The article begins with a comparative literature review on the topic, before discussing the results of several cyclic loading tests on a sample of sand, with the results showing that an increase in frequency of loading caused an increase in the liquefaction resistance and a decrease in excess pore pressure, especially in the denser sand samples.
The Stamopoulos conducted research into the effect on cyclic soil strength under the application of various levels of pre-stress. From their research, it was found that the pre-stress increased the strength of the soil, especially in samples with lower densities. In summary, they found this improvement in cyclic shear strength is due to pre-stress causing an increase in density and horizontal stresses, whilst changing the soil fabric so that the particle contact area has increased. They also proposed equations to calculate the effect of pre-stress ratio on the soil shear strength by considering the strength after 15 cycles for both pre-stressed and non-pre-stressed samples. Written in 2011, this paper investigates the relationship between the cyclic loading effects of earthquakes on the effective stress of sand. Throughout their research, Matsuda et al. Simulated earthquake action through multi-directional shear tests and found that the shear strain amplitude has a large impact on the effective stress of granular materials, and that cyclic strain and pore water pressure increase with the number of loading cycles, whilst the vertical effective stress decreases. Additionally, they proposed a pair of equations to determine cumulative and resultant shear strain in a soil, which have been used to investigate effective stress changes of granular materials under undrained cyclic shear conditions.
In the article written by Ajmera, Brendan, and Tuari, clearly conveyed the characterization of the reduction in undrained shear strength in fine-grained soils due to cyclic loading. They used both simple shear and triaxial tests and found that the influence of excess pore pressure at the end of the cyclic loading resulted in lower post-cyclic undrained strength ratios. The degradation of undrained shear strength increases with cyclic loading, whilst the plasticity index of the soil decreased. They also found that post-cyclic undrained shear strength with respect to post-cyclic effective stress ratios resulted in the cyclic undrained shear strength ratio of the soil subjected to cyclic loading being greater than the undrained shear strength of the ratios of the normally consolidated samples. The post-cyclic effective stress ratio and normalized undrained strength ratios were calculated using the equations 1 and 2. In the paper written by Raghuvandan and Janenja, they illustrated that by the diagram on the right, we find soils tend to behave better under cyclic loading and can withstand a substantial amount of cycles and therefore are far less susceptible to liquefaction. Whereas compared with sand, which withstands a lower amount of cycles and therefore more susceptible to liquefaction.
As briefly introduced in the various literature reviews, there are a number of factors which affect the cyclic shear strength of a material. The direct mathematical relationship to calculate shear stress is presented on the screen and is seen to be directly dependent on the soil's cohesion, mean effective stress, and friction angle. By investigating these factors further, it is found that they are also influenced by properties such as the soil material and density, poor water pressure, principal stresses, and the number and frequency of the applied loading. Additionally, as seen from the depicted graph, a soil's peak shear strength isn't maintainable, so under increased loading, a soil's strength will constantly degrade until it reaches a stable residual strength. The same concept applies for cyclic loading, as when the strength of the soil reaches a level corresponding to zero effective vertical stress and large cyclic shear strains, the soil shear strength will decrease significantly and liquefy, posing significant risk to infrastructure. As summarized in the preceding literature reviews, the cyclic strength of soils increases with pre-stress and is most effective for low-density materials. In addition to this, preloading is favorable as it is one of the cheapest and simplest means of soil improvement. In 2007, the Stamopoulos developed a pair of equations to describe the relationship between the pre-stress ratio and the shear stress ratio after the application of 15 load cycles, which can be applied with different exponents to satisfy different preloading conditions as per the figure on the screen. This is important for engineering practice as it allows for the simple calculation of the amount of pre-stress required for a soil to attain a suitable cyclic shear strength for application underneath a repetitive loading scenario such as traffic or earthquakes. Additionally, it has been found that preloading influences the cyclic strength of a soil as it increases the density and changes the fabric of the soil sample by promoting larger areas of particle contact. The figures on the screen clearly depict this relationship as the samples that received pre-stressing prior to loading all displayed a larger resistance to cyclic shear stress, whilst also showing that overall the samples with the higher void content had less of a decrease in shear strength from initial to failure conditions, whilst denser samples had an overall increase in cyclic shear strength.
Currently, the majority of cyclic loading prediction is based off implicit models, suitably for relatively low number of cycles. However, there aren't currently many explicit models for high cycle observations of soil under cyclic loading. This is significant because while the strain accumulation rate was found to increase proportionally to the square of the average strain amplitude and independently to the number of cycles, the increase in cycles has been found to cause an increase in pore water pressure and hence a decrease in the shear strength. Loading frequency is shown to have negligible effect on strain amplitudes of soil samples tested. However, it has been found to have a significant effect on the liquefaction resistance of the soil. Liquefaction is a phenomenon where the pore water pressure within soil is increased to the point where the soil particles can move freely relative to each other, and is commonly caused by the ground shaking from earthquakes. An important factor that has been noticed is the soil liquefaction resistance, a value that is affected by the number of loading cycles, the density of the soil, and loading frequency. As the loading frequency increased, the cyclic stress ratio difference between loose and dense sands increased up to 82%. It was also noticed that liquefaction was reached after a larger number of cycles for a higher loading frequency. Another factor that was noticed to impact the liquefaction of the soil was the initial vertical stress of the sample, with a higher initial vertical stress causing a lower liquefaction resistance, especially in the denser soils, as can be seen from the graphs shown.
Another main influence is soil type. Soil type is influenced by the soil friction angle and is the measure of a soil ability to withstand shear forces. Different soils have different soil friction angles and therefore different strengths and plasticity characteristics. Soils with high plasticity indexes show decreases in the undrained shear strength ratios, whilst low plasticity soils show increases. We can see through vigorous testing that soils with high plasticity show a decrease in the post-cyclic undrained shear strength ratio and are more inclined to fail under repeated cycles, whereas with lower plasticity indexes showed a higher post-cyclic undrained shear strength ratio and are more inclined to hold their integrity under repeated cycles, making for better footings. In the paper written by Tijwari and Brandon, we see that there are two main methods used: the Norwegian Geotechnical Institute simple shear apparatus and the cyclic triaxial test devices. The main differences between the two test devices are that triaxial tests require the soil to be prepared by a certain method, as undrained sand prepared by compacting showed greater resistance than by air pluviation. There was no difference in preparation method for simple shear apparatuses. There was also no difference in the results for the two test methods when using air pluviation for loose to medium specimens. There may be an overestimate in liquefaction strength for cyclic triaxial undrained tests of damp to moist soils. Therefore, because there was no difference in the method for simple shear apparatuses, we can see that the simple shear apparatus may be more suitable to determine the shear strength.
Due to the effect of loading frequency on the soil behaviour, these cyclic loading tests are important in planning for earthquake actions, as different earthquakes have different frequency effects on the soil. Liquefaction resistance is an important factor to understand, as loss of shear strength of soil beneath structures can cause catastrophic building failures, such as the building failures shown here due to liquefaction after the 1964 Niigata earthquake. As discovered in the investigations, dense soils are preferable in earthquake-prone areas, as they have been found to exhibit a higher liquefaction resistance than loose soils. Another solution to increasing the shear strength of soil foundations is the addition of chemical admixtures into the soil. However, these admixtures have been found to cause the soil to act excessively brittle under cyclic loading, and hence don't increase performance as they are supposed to.
In conclusion, as above, you can see that we have illustrated a keen understanding of the focus area of shear strength in soils and how different factors such as cyclic loading affect shear strength. This is evident through the literature reviews and further exploration into factors such as preloading, frequency of cycles, liquefaction, soil type, and testing methods, and how they each affect shear strength outcomes. We've also illustrated how shear strength is affected due to cyclic loadings in engineering applications.